Hi, everyone. It's pretty exciting to present something here, and I'm really happy to be on this place today, to see you all here. And I will try to make my talk as interesting as possible and to share some tricky stuff about gaming in the browser. So who am I? My name is Alex. I'm software engineer at EPAM Systems. It's a company which provides software engineering consultancy. I have recently moved to Los Angeles from Belarus, as Ben mentioned. It's a country which is almost in the center of Europe. I'm active js.la meetups listener. I like to solve different tricky challenges in my spare time, and I support open source. And why I'm here? I enjoy js.la meetups, and everybody shares knowledge with me. You share knowledge with me, and it was some kind of Call of Duty inside. And at that time, I was playing with graphics in the browser, and I decided, why not to try to share knowledge with you? And that's why I'm here. I have a small disclaimer before my presentation. There will be almost no code. So initially, I included some pieces, but talk becomes really very huge, so I removed everything. But for those who are really interested, I added some useful links in the end, and I did not minify code in examples, so feel free to check it. So if you're ready, let's dive into my tricky journey. The first question I met, which instrument to use in browser for gaming? I could use videos, static images, canvas, SVG, and WebGL. And as you have already probably guessed from the slide, from the logo on the first slide, I decided to go with WebGL. So what is WebGL? WebGL is just JavaScript API. It's not NPM package. It's just API which is accessible after getting WebGL context from canvas element. WebGL is designed for being used for 3D graphics. WebGL is rasterization API. It's not 3D API. It means that there are no methods like draw cubes or something similar. It's rasterization work. WebGL is cross-platform API. So you should not care where your code will be ran. WebGL is really performant on a huge amount of objects. And it is supported on all modern mobile and desktop browsers, such as Chrome, Safari, Firefox, and IE 11+. But it has quite steep requirements for entrance. So the first thing I realized that WebGL is just positions and colors transformations. That's all. And it has great performance because it executes your code, your entity, on GPU. And that entity is called program. Program itself consists of two functions. The first is vertex shader, and the next one is fragment shader. So as I said, WebGL is positions and colors transformation. So vertex shader is responsible to compute vertex positions. And fragment shader itself, its job is to compute a color for each pixel, which you see on the screen. All WebGL can do is just draw three primitives: point, line, triangles. No rectangles, no cube, or something similar. If you want to create something different, you should use combination of these primitives. For instance, if you want to draw a rectangle, you should use two triangles. And one more important thing, that WebGL only cares about its own clip space coordinates. It goes from -1 for 1, 1, and the same one for 3D, And it's no matter on your canvas and screen size, and any point outside this area will not be drawn. So at that moment, that was enough for me to understand the concepts, and I decided to create my own hello world. Each technology has its own hello world, and for WebGL, it's drawing one of that primitive. I decided to go with triangle. So here is how it looks like. Here I'll show some code. Do you see something? So what I do here, I just pick positions from my range inputs to positions. They are in pixels. I pick colors from color pickers. Here is some magic with clearing canvas and uploading data to GPU. And here the method like render draw arrays with primitive type triangle. But the most interesting here is those shaders. Shaders are functions which are written in GLSL language. It's OpenGL shading language. It's C-like, strongly typed language. So as you see here, I pass two attributes. It's like my positions and colors. I pass resolution because I need to transform from pixels to WebGL clip space. And here is my transformation. And here I set the position to the global variable, GL position. It's some kind of return function, return value of any function. And here is fragment shader. I just simply pass color here, and the same as in vertex shader, I just set that value to another global variable. And let's play a little bit with that. So if I change here some attributes, so like this, I just change my vertex positions. And let's change colors. First, and for this. So if you see, like, it's linearly interpolated. It's pretty cool, as for me, but we're still using JavaScript. And as you see, there are 4 ways how shaders can receive your data from JavaScript to GPU. Like, the first one is attributes and buffers. This data type is used for passing your data per each vertex. The second one is uniform. Uniform is just global variable, which is used for everything, like one color for everything, or as I passed screen resolution for transforming to WebGL clip space. The next one is texture, which is usually used for images, but it's just array of data. And the last one, varying. So attributes and buffers could be received only in vertex shader. And if you want to pass data from vertex shader to fragment shader, I should use varying. And here's how like rendering pipeline looks like. I pass some data, some coordinates in pixels. In vertex shader, I transformed to WebGL clip space vertices. Then there is shape assembly work, which decides like which borders my primitive will have. Then there is rasterization work, which decides which exactly pixels on your screen will be used for drawing your primitive. Then there is fragment shader work, which decides like which color will be used for each pixel. Then there is test and blending work. For instance, like there is depth test. If you have like in 3D space 2 points and one is more far from you, it will be skipped. And finally, you get just 2D array of color positions, and you see that output buffer on your screen. But I didn't stop on that. It's just primitive. The next challenge I got is just drawing something different from primitive. It was a circle. There are many ways how you can do this. I decided to go with this solution. So I just pass coordinates per each vertex of triangle. I pass the coordinates of the center of my circle and pass radius. And as shaders are executed per each pixel, I just see if the distance between the center of circle and that pixel is more than radius, I skip it. If it's less, I draw it. And here's how it looks like. So it's just simple circle. And here, let's try to increase the radius. And here we could see that it's still triangle. Some kind of tricky. For creating game, I definitely need some interactions. So that was my next goal. What I got here, it's some kind of, I called it iter. So I can move and pick some dots. Yeah, and important thing here that the circle doesn't change its shape. So, and I pass attributes for drawing this circle. So changing attributes on GPU is pretty expensive operation. And for manipulating the position or something like this, we should use uniforms. It's quite quick, yeah, you know. Okay. So there are highlights which I got on that moment. The first, I really realized that I use just triangles to render. I upload data attributes once, and whenever possible, do not change them. I use variants for passing data from vertex shader to fragment shader. And the last one, it's collision detection. As you see, like dots disappear when they intersect with circle. Here is how I did it. So here is just some dots on the screen, and here is a circle. And we could easily calculate collisions on CPU. Yeah, just iterating over all dots and see which of them like inside my circle. But it's not interesting because we are using GPU. And there is API in WebGL which provides ability to read different pixels from the screen. And that is what I did. I get index of each dot, encoded it to hex, and it was the color of the dot. So I just read the pixels from my circle, decoded that colors to the indices, and just removed that dots. So you see that here are different colors per each dot. And that's almost everything about WebGL, but I still want 3D. It was just 2D. And migration to 3D is pretty simple. It's just adding one coordinate, Z coordinate. What I did the first, I went to Blender program to create 3D model. It was a sphere. And you see here it consists of rectangles, but as WebGL works just with triangles, I triangulated that model. Then I saved it to, then I saved it to opsh file, which actually consists of just coordinates, vertices of all this model, and upload it to WebGL. Quite easy. This was my first attempt. Not very pretty. But then I fixed everything, and everything is OK. And here is how the sphere looks like. So you see, I just colorized with random colors, all triangles. But it's sphere, but it still consists only of triangles. The next point, let's say about objects in real life. Let's say like a table. When we go farther, it's like scales. It becomes less. When we like rotate our head, it rotates as well. But like the shape of that object does not change. So we should not change attributes. We should control everything using uniforms. And I had to recall some math from my university and make transformation matrices for that. So if I want to scale object, I just should get this scale matrix and multiply my attributes on that matrix. And my first what? Really? I need to do that stuff? But fortunately not. Other guys already created a great library for these purposes. And if I want some metrics, for instance, for scaling, here is the method which returns my metrics, and I just multiply on it. So I do not care about all that math. Transformation is OK. But what about lighting? The real world consists of a lot of different lighting tricks, like shadows, something similar. Before we go to that, to be on the same page, we should know what is a normal. Normal is a vertex which is perpendicular to your surface. And with lighting, I didn't read any tutorials. I just decided to go with my own solutions. And I dived into experiments. I highlighted 3 points which affect lighting. The first one, it depends on the angle between the normal of surface and the direction of the light. So it looks like that. Oh, do you see? So if light rotates, surface becomes darker. The next point, it's distance between the source of light and the surface. So if we move it out, it becomes darker. And the third point, it depends on point where your light directs. So it looks like that. So after these experiments, I combined all these solutions into one and used for my custom solution for lighting. And the last thing for the game, but not the least, it's interactions movement. So the first point for that, I called it state instead of events. It means that we should not react to event listeners, like if key is pressed, we update position. We should have state of that, like left key is pressed. And when the state is true, we just update our position, for instance, in request animation frame, because it's used to update an animation before the next repaint for being our animation smooth. And who knows the movie Harry Potter and the Goblet of Fire? Oh, nice. OK. I was a little bit inspired by the maze of there, and I decided to create something like that. Not so awesome as in film, but anyway. And for like level generation obstacles, I just use simple txt file. So like x, it's obstacle, and 0 is just empty space. And what is I finally got? So it's still in development. I want to add some different features, but here's like it looks like. So we see all the maze, we see where is the goblet, and our task is just define that goblet. And here you see the lighting, that points which I talked about. We go like, oh, because screen resolution is so slow. Oh, not here. Oh, where is it? I lost it. Oh, it's here. Oh, OK, cool. I found the goblet. Thank you. It's also supported on mobile browsers, so like this. Oh, we should wait, yeah. So for interactions here, I just added some joysticks. Yeah, so. It's not very convenient from the desktop, you know. But anyway, like, here's how it looks like. So you see lighting here, and the obstacles are just passed via attributes. They are static. And for the movement, here, I'm like a camera. So I just update like perspective transformation metrics and just pass it to GPU. So it's pretty simple. OK. So here is like some summary, which like based on my experience. So the first, like WebGL is just rasterization API for rendering 2D or 3D objects. It's not 3D API. The next, WebGL uses shaders as functions which are executed on GPU. That's why it's so performant. WebGL can render only 3 primitives: point, line, and triangle. If we want something different, we should combine these primitives. Any transformation can be achieved using transformation metrics. We shouldn't change like attributes. Models could be generated and easily used in WebGL, like OPT models. It really consists only of vertices, so it's like a friend of WebGL. We shouldn't change attributes. I already mentioned that. Try to control everything via like uniforms. And the main one, don't worry, it's not so hard as it seems to be. It's really very funny and tricky. Here are some exciting things which I promised, but unfortunately not enough time for today. And thank you very much for your attention. Here is presentation links and QR code for that. And I'm on social media. Feel free to add me, ask questions.